Okay, let's look at an example of correlation data. If we were to collect two sets of data, in this case years of experience that people have in their income in thousands of dollars, we end up with this table like this. They have experience in years, their income in thousands. So this is like, for example, with no years experience, your starting salary is $20,000, and for subject number 10 who has 35 years experience, their income is $60,000. And what we want to know is if there is a correlation between these two things. So the next question is, it asks what kind of information is included, and what form does it come. So if we look at that, there's not a yes or no information. It's all years experience and income in thousands of dollars. So it is raw data. So we know from that that we can use what's called a Pearson's correlation. Ask how many comparisons can we make? Well, we only have two sets of data. We only have their years of experience or income in thousands of dollars. The subject number is just a way to keep track of it, and their subject number obviously is not going to have any effect on those other two sets of data. So we can only get one correlation. And what we end up with is something like this. So for each of those data points, for example, here was the person with 0 years of experience in their income, 5 years experience in their income, etc., etc. So we can see how these are related to each other. This line going through the middle, if you'll remember back from your math classes, is called the line of best fit. And that is the line that best defines the relationship between these two sets of data. This is a visual representation. However, that's often not enough. One of the questions that's on here is there anything else we would like to know? Well, what we would like to know is this. Is this a true relationship? Is there really a relationship between the number of years experience that people have and how much money they make? Or did this data that we get just occur by chance? What allows us to make that decision is this, is the significance number. The magic number for any of the data that we look at is what's called a 0.05. If this number, this p-value, is less than 0.05, that means that the relationship is a significant relationship. It didn't occur by chance, that we can be relatively sure that what we saw happen really did happen. The other value we'll get is called this R value. Correlations always have a set of numbers. They can range from -1 to +1, and zeros in the middle. The higher this number is, the closer this number is to 1, then the better the correlation is, the stronger the correlation is. This number can also be negative, and all that means is it's a negative, or it's an inverse correlation. As one number goes up, the other number goes down. And those two numbers, to have a positive correlation or a negative correlation is okay. We can have weak correlations. We can have no correlations. So we want to look at whether or not there's a relationship, how strong the relationship is, or how strong the correlation is, and whether or not that correlation is a significant one. The other number that you'll see sometimes is this R squared. This is called explained variance. Well, if we look at this number over here, if the best we could have is a 1, that means there's something we don't know about this relationship. So one of the things I ask is to make better use of our data, we want to collect information on one other thing. Well, there's more information there we'd like to keep track of. This number is what is missing. If you take the 0.858 and square it, you get 0.74. That's called explained variance. If you subtract, and that means that this explains 74% of the relationship between income and number of years of experience. But that also means that 26% of that relationship we haven't been able to define. There's one other thing somewhere that we didn't keep track of, or maybe more than one other thing. For example, education. might be defining that relationship between these two things. Now, what happens is this. There are several representations that can come up. What I want you to do is look at these charts and understand the fact that you can have a positive correlation that's significant, a negative correlation that's significant. You can have no correlation. You can have a weak positive correlation. That means that the numbers are kind of spread out around the line. You can have a weak negative correlation. And what that means is there's more variation. The numbers are further away from this line of best fit. Some of the correlations that we could think of are, for example, there's a relationship between the cost of a diamond and the number of carats. So going back to this, the more carats a diamond has, the more it costs. There's an inverse relationship between how old your car is and what it's worth. And of course this would depend upon the scale. If this was $20,000 up here and 0 here, and this is the age of the car, as the car gets older, it becomes worth less. Except for, and there's always an exception, there are some cars that will do this. They'll have a U shape to them. Another example of this U shape is test anxiety and performance on a test. Students that have high test anxiety or low test anxiety may not do very well. Actually, that would be the other direction. And what that means is students that have high test anxiety may not do well because they're so uptight about what's happening that they may not do well on the test. Students that have very low test anxiety who just don't care may have low scores too. Another example of a correlation is the amount of money you make and the number of years you've been in school. In general, the longer you are in school, the more money you can make. However, there are always exceptions to that. There's people who get PhDs in English who don't make very much, as opposed to somebody who goes to diesel mechanic school who can make quite a bit. So that doesn't always work out. Other examples of correlation are exercise and heart disease. In general, you would think as one goes up, the other would go down. The more exercise you do, the less risk that you would have a heart disease. Of course, there are exceptions to that. Think of Jim Fixx, who is an expert on running, who died of a heart attack while he was running. Weak negative correlation might be exercise and score on a depression scale. Yeah, they might be related, but there's more to not being depressed than just exercising. Miles ran per week and weight loss. The more miles you run, the more weight you lose. Well, yeah, there's probably some correlation to that, but there's more about it that we don't know. A weak positive might be hours spent studying and grades. So let's look at this. The more hours I spend studying, the higher my grades will be. Well, as we all know, that's not always enough to do well in a class. There are other factors. How important school is to you, general intelligence to start with. So there's some things that we don't know about, and that's what is the difference between a relationship and cause and effect. The next thing I want you to do is to go to the discussion boards and provide some examples of positive correlations and negative correlations. So I just want to make sure that everybody has an understanding of a relationship between two sets of data. So you'll see some places that you can enter some information in there.